Okay, so now we're going to move on to electrochemistry in general. So an electrochemical cell is a system that has two electrodes. The electrodes are generally metals, but not always, but sometimes they're usually metals. They're dipped into an electrolyte solution, and the electrochemical cell can either generate electricity or will require electricity to make it go. So it's either going to go one way or another. A voltaic cell, or also sometimes called a galvanic cell, is an electrochemical cell that happens spontaneously. So it will generate an electric current. So this is a reaction that will happen, and electrons will flow from the anode to the cathode. It will be a natural process, and so it's spontaneous. The other kind of cell, which is which does not happen spontaneously, and the only way it can happen is if we put electricity in to drive it. You can sort of think of it as, here, if you have a battery, it spontaneously gives you energy, but when it runs out, if you have a rechargeable battery, then you have to charge it in for it to go backwards to recharge. And so this would be an electrolytic cell, is one where you have to put electric current in to make the reaction happen. Otherwise, it's a non-spontaneous reaction. If you just stuck it together, nothing would happen. You have to add electricity to make it happen. So keep those names in. So mostly we're going to talk about voltaic cells, the ones that are spontaneous. And like I said, the only way you can get the electricity, it can happen spontaneously, but the only way that you can collect the electricity or use the electricity is if they're in two half cells that are separated from each other. And so each half cell has the half reaction for either oxidation or reduction. And they have to be connected in some way to make it, but each cell is separate. So a simple half cell is made from a metal strip dipped into a solution of its metal ion. So for example, if you have a silver metal dipped in silver ion, or copper metal dipped in copper ion, or iron metal dipped in iron ion, etc. Zinc ion half cell will have a strip of zinc metal dipped into a solution of zinc ions, or zinc salt. So the negative ion is not going to be, it's just going to be hanging around. Here's another example, a copper strip dipped into a solution of copper salt. So the voltaic cell, which is the one we're mostly going to focus on, has the two half cells that are electrically connected. What I wanted to, before I show you this, if we have, we looked at this reaction back in chapter 4. If we have zinc metal and copper ions, and if you just stick them together, so let's say you have a container and you stick a piece of zinc metal, and we have some, let's make this blue. We have like a copper solution here, and we stick a piece of zinc metal into it. Well, and I know I think first semester we look at this reaction, and actually what happens is the copper metal starts to plate onto the zinc metal. The copper ion will start to form copper metal, and at the same time the zinc ions will come off. I can't draw it very, let's use purple. The zinc ions will come and get into solution. So the zinc metal will oxidize and become zinc ion and come in solution. The copper metal is reduced and starts forming, and so you start getting like a coppery color metal. The metal, it's like you're plating, and we'll talk about that in a minute. So you're getting like a cover of copper, and at the same time this solution starts getting lighter and lighter because the copper is being used up. So you may or may not remember that. And like I was just saying a minute ago, if we did all that in solution, this is a spontaneous reaction, so that will happen, but we're not going to get any electricity out of it because this is all happening in one solution. So in order to create a cell that actually gives us electricity, we can take those two half reactions, and here we have our zinc going to zinc ion is 1/2. That's our oxidation reaction, and our copper going to copper metal, and they each have 2 electrons, and so that's our reduction. If we separate them into two different containers and connect a wire between them so that, and it's an external circuit, so that the electron has to flow outside of the cells, that's when we can get electric flow. And so let's look at this copper zinc voltaic. So you can see here what we have. We have a piece of zinc metal instead of having it all combined into one container. We have a piece of zinc metal, and it was originally like that, and we had a piece of copper metal. I'm not very good at drawing that, but I guess we'll go here like this. It originally looked like that. There we go. And this, on the left-hand side, we have our zinc being oxidized to zinc metal. So there's already some zinc ion in solution here, but then a lot more of the zinc will be oxidized and it will go into solution. So you can see that the zinc electrode is starting to wear down because it's forming zinc ion. On the other side, the copper is being reduced, and so the copper ion is gaining electrons, and then it's kind of sticking itself to the copper, and so you can see the copper metal is actually getting a little bit bigger. So the copper metal is still being reduced and turning into the copper ion is becoming copper metal, and the zinc metal is becoming zinc ion. But now, because they're separate, we can actually have like an external circuit where the electrons flow. So the electrons will, since zinc is being oxidized, the electrons will leave this cell and they'll travel through the wire and they'll end up coming into this cell where now the copper is reduced. And this will happen spontaneously because this is the natural flow of things. And we actually have to have some kind of internal, eventually this would stop, because if you keep putting negative charge from one to the other, it'll eventually stop because your charges have to stay balanced. So what happens is we have what's called a salt bridge, and the charges can rebalance each other, and these are ions that are not part of the reaction. So we might have some like chloride ions or potassium ions or something like that that are moving back and forth just to keep the charges balanced. And so that's what a voltaic cell is. And as long as there's an external circuit, the electrons can flow from one electrode to another. In this case, because zinc has a greater tendency to lose electrons than copper does, the electrons will flow from zinc to copper. So the zinc atoms will lose the electrons, which we know is oxidation, and the copper will gain the electrons, and we know that's reduction. So the electron flow will go through the external circuit to the copper, where the copper then gains the electrons and become reduced. And so we're able to have that that connection. Then the electron flow is what we can collect as electricity of some kind. The two half cells, like I said, also have to be connected internally to allow ions to flow, because otherwise, like I said, too much positive charge builds up in the zinc half cell and too much negative charge will build up in the copper cell, and that will cause the reaction to stop. And so we have to have some other ions, like I said, maybe not involved with the reaction at all, but other ions that can flow back and forth to balance the charges. And we call that a salt bridge. So it has positive and negative ions that can move to balance charge. And so here's that same reaction, or that same cell, a little bit showing it a little bit more in a little more detail. So over here on the left-hand side, we have the oxidation happening, and the oxidation is the zinc becoming zinc metal and losing 2 electrons. The electrons are flowing out of where it's being oxidized. We can get some work out of it, like light up a light bulb or whatever. The electrons keep moving. They go to to where reduction is happening, and you can see here that there's a buildup of the copper metal. There's a wearing down of the zinc metal. If you were to watch this for a while, this copper would have started out as a dark blue, and eventually it would fade to a very light blue because the copper is being deposited. And you can see here, this is called the salt bridge, and so it's got some other ions that aren't involved in the reaction, and they're plugged, but the ions themselves can still move through here, and so the charges end up balancing. As we said, this is the oxidation. Oxidation is where the electron flows. The oxidation, the electrode where the oxidation occurs is called the anode. Since the oxidation is giving off electrons, we're going to label the anode as negative. So the electrons flow from the negative end to the positive end because electrons are drawn to the positive end. So that's why we label this side the positive end, because the electrons are moving to it. And the reduction half cell is called the cathode. The way I always remember it is because these are both consonants, cathode and reduction, anode and oxidation. The two vowels stick together, and the two non-vowels, consonants, stick together. So like I said, the salt bridge is just a tube of electrolyte. It's usually in a gel, and it's stuck into the two ends of the half cells. And so the salt bridge allows the flow of ions, but prevents the mixing of the two different solutions. And so there's no direct reaction. Like I said, either KCl, sometimes NaNO3, KNO3, a lot of these salts that aren't involved in the reaction are in the salt bridge. And like I just said again, the anions flow toward, oh, no, I didn't just say this. So if the anode where oxidation takes place is more negative, and the electricity is flowing this way, so the electrons are leaving the anode, and so it's becoming more positive. And so in the salt bridge, the negative charged particles have to move toward this side to try to balance it, and the positive ions have to flow in this direction because this side is becoming more negative because the electron flow is gaining more electrons. So this side has to be neutralized with positive charge. So that's within the salt bridge. The salt bridge. I think you can see that on the previous picture. And so here's an actual, so here's our salt bridge that's filled with the ions that aren't involved. We've got our zinc solution here, and we've got our copper solution here. We've got our copper metal and our zinc metal. And in this case, the electrons are flowing. It's kind of the opposite side from before, but the electrons are flowing from the zinc. Here we're measuring the flow. Since it's positive, it's going in this direction. There's a lot more to it, and we just don't have time to get into all the details. But anyway, the electron flow is in this direction. If we needed it to go in the opposite direction, which is not spontaneous, we'd have to actually put electricity in to make it go the other way. So again, the two half cells are noted. The oxidation half cell, we already saw this, and the oxidation half reaction is called the anode, and the reduction is called the cathode. And then when we add the two half reactions back together, we have the overall. This is the net reaction or the cell reaction. And this is always after the electrons are balanced, so we don't see any electrons in the overall reaction, because the same number of electrons that leave have to be gained, that leave the anode have to be gained by the cathode. So electrons are given up at the anode, so that's why they flow from the anode to the cathode. So we label the anode negative because that's where the electrons are starting, and they're going to the cathode, which is positive. So the electrons are flowing from the anode to the cathode. Yep, that's what I just said. So the anode has the negative sign and the cathode has the positive sign.
Okay, so let's look at an example, and let's try to create a voltaic cell, and let's look at the options here. There will be a half cell where a copper metal rod is inserted to a solution of copper nitrate, so copper ion and copper metal. Oops. And then another half cell with a silver metal inserted into silver ion. And then they're connected by a salt bridge. And then when they're connected to the external circuit, this is important, the copper is oxidized. So far we don't know how to tell if that's true or not. So copper is oxidized, so we realize that that's the anode. So let's sketch the resulting voltaic cell, label the anode and cathode showing the corresponding half reactions, and then indicate the direction of electron flow, and write the complete cell reaction. All right, so this is what it looks like, and we can see that we have over here we have the copper ions and the copper metal. It's the anode because we know that copper is being oxidized. Silver is being reduced, going onto the metal. So this is the cathode. So the oxidation is copper metal going to copper ions plus 2 electrons. And then the silver is going from silver ion, gaining an electron, and going to silver metal. So that's the half reaction at the cathode. That's the half reaction at the anode. Here's the salt bridge. It doesn't really, you don't have to put what the ions are, but the salt bridge is there. And we always know, let's see, oxidation is always the negative because that's where the electrons are coming from. The electrons will flow toward the cathode, and then the cathode will be positively charged. And so then to write the complete equation, we have the copper going to copper ion. We have the silver going to silver metal, silver ion going to silver metal. Notice that to get the electrons to cancel, we have to multiply the second equation by 2. So the electrons will cancel, and we get our complete cell.
There is a shorthand way of designating voltaic cells, and so let's look at that. So if we go back to our example where zinc ion, and copper will be written like this. So the anode is always written on the left where oxidation happens, and the cathode is written on the right. Notice that the metals are on the outside. So this is like, so if I were to draw this, I'd have like a zinc. This would be zinc. We saw this is what we saw earlier. This is zinc ion. And then we've got a metal to the copper solution with the copper metal. Right? This is how we would write it. So the zinc metal going to zinc ion is on the left-hand side. I'm going to go ahead and erase that so you can see that better. And then, so like I said, the reduction goes on the right-hand side because it's actually going from copper ion to copper metal. It's kind of going in the direction it's showing. We write, let's go ahead and erase that so you can see. So the anode, like I said, is written on the left. The cathode is written on the right. The two electrodes are connected by a salt bridge, so we indicate that by a double line. And you can see that each terminal, so the metals are the terminals. The metals go on the outside. And so as you can see that the single vertical bar then indicates the phase boundary just between the solid and the electrode solution. And notice a lot of times you'll see AQ, meaning that it's an aqueous solution. Sometimes you'll actually see a concentration written on, like what you'll see on the slide. So a lot of times you'll have to do concentrations. Or if there's a gas, which I'll talk about in just a minute, you might see the pressure for a gas. And so some metals are some are not metals, and so you can't have a metal solution or a metal like hydrogen. Like I said, we'll talk about that. But a lot of times you'll see a little bit more detail, either concentration or pressure. So in this case, you can see that since this is the anode, so zinc is becoming zinc ion, and that means it's losing 2 electrons. In this case, now even if you didn't know anything, notice that this actually has 3 lines. There's a phase boundary. We have our aqueous H+, we have our gaseous H+, or H2, which is but H2 can't be an electrode because it's not a metal, and so platinum is actually our electrode metal, which is inert. And so again, I'll talk about this in a second, but this reaction is going from H+ to H2, and so to balance that we need 2 here and we need 2 electrons. So these are our 2, you can kind of pull out the half reactions that are happening, the oxidation on the left and the reduction on the right. So like I said, if a half reaction involves a gas, we need some kind of inert material such as platinum to serve as the terminal, so that there's some kind of surface for the reaction to occur. So a hydrogen electrode, one of the most common electrodes, is where hydrogen gas bubbles over a platinum wire or platinum plate, and it's immersed in a H+ solution. So like I said, that's the cathode half reaction. And it looks like this. So even though the platinum metal, you can see here, this is the platinum metal. The platinum metal is inert and it's not involved in the reaction, but in this tube, it's got hydrogen gas flowing through it. So we have hydrogen gas and hydrogen ions. So the reaction is where the hydrogen ions are gaining electrons, and it's actually forming gas and leaving. So because it's not a metal, it can't stick on the platinum, but it is formed. If it happens to be where the hydrogen is being reduced, so it's written as a cathode, you can see it's in this direction with the platinum wire on the outside, the hydrogen gas inside that, and the hydrogen ion. If it happens to be where the hydrogen gas is being oxidized, then it's written in the reverse direction. So this would be hydrogen gas becoming 2 hydrogen ions, so this would be oxidation of hydrogen gas, and this one is reduction of hydrogen ions. And so so if you're always writing in the same way, you can figure out the left-hand side shows sort of the oxidation. So this would, if it was an anode, then you'd have the other one over on this side. If it's the cathode, then you have the other electrode on that side. So, and this is not true just of hydrogen, but of any of the metals. So the outside will always be the metal, and the inside will be the aqueous solution, and it will you just kind of read inside, but it kind of helps you see which direction the reaction's going. Here's some other examples of electrodes. So a chlorine-chloride reaction, since chlorine is also a gas, also needs a platinum. So this would be chlorine gas being reduced to chloride ion. In this case, you don't actually have, this is a metal +3 ion going to a, I'm sorry, iron +3 going to iron +2. So it is being reduced, but notice that there's no iron metal involved in this reaction. Here's the reaction over here. And so again, platinum will be the wire where this reaction occurs. So you only use the actual metal that's involved in the reaction if it's as the electrode if it's involved in the reaction. So here's tin. Tin is a solid, so you can have a tin electrode and a tin ion. And so most of the time you'll just see it like that. But again, if there's no metal involved in the reaction, usually you'll have platinum or sometimes palladium, PD, as the inert metal. All right, so let's write the overall cell reaction for this voltaic cell. And for a little extra, we're going to go ahead and write the draw the cell, what it looks like. All right, so like we said, the left-hand side is always the anode. So that means it's oxidation. And we can go, it kind of goes in this direction. So that means cadmium is becoming cadmium ion. And in this case, that means 2 electrons are given off because it's oxidation, because it's going from 0 to +2. We have to add 2 electrons. This side, this is my reduction, so that means electrons are being added. But again, if we kind of follow the flow, we've got hydrogen ion going to hydrogen gas. And because the first thing we want to do is balance that. And then in this case, the hydrogen ions have to gain electrons. In this case, it happens to be 2 electrons. So here's our reduction reaction. And now we can write them, we can add them together because there's 2 electrons on the left and 2 on the right, so they cancel. So let's see what those show. Okay, so we have our cadmium going to cadmium ion, our hydrogen ion being reduced. If we add those together, then we have our full cell reaction. We could draw the actual picture. This side would have cadmium metal. I didn't leave myself enough space. So here we have cadmium ions. We'd have the connection. In this case, because we'd have hydrogen ion in here, we're going to have the electrode with a platinum wire. And then it's going to bubble hydrogen gas in there. So hydrogen gas will be in there. So, and then if we need to, we know that this is the anode. The anode is negative. So that means electrons flow in this direction. They're not always written left to right, but if you have this kind of symbolism, then it is left to right. The anode's on the left, the cathode's on the right. If you're just given information like we were before, you may not be able to figure out which is which until you actually figure out the reactions. But this side is positive. This is the cathode. And anyway, that's what our cell will look like. All right.